Okay. Let's go over exam number 1. Whoops, did I not bring the pencil? Sorry, I don't have my, I thought I had grabbed my special pencil. I will have to pause the recording because okay, there's a quick question. My office hours have already elapsed, so you'll have to wait till Thursday or we'll set up a time. So, okay. Let's go over the exam, and I'm not going to give the answers. I'm just going to work out the variables because I think you get a lot more information when you work out and show the variables because the numbers sometimes you get buried with stuff. So the first problem is you have 2 substations with an impedance across the interconnecting substations, and you have a bus voltage on here and a bus voltage here, and then you have a impedance. And it says the phase voltages are as noted, right? These are phase voltages, not line voltages. These are phase voltages. So the first thing is, what is the complex power that is being transmitted from bus 1 to bus 2? Well, if you want to solve for S at bus S flowing there, it's just VB1 times I conjugate. That is the current. That total power that is going from bus 1 into the transmission line, as well as being delivered to bus 2, has to be carried by the current, right? So you have to solve for I, which is VB1, minus VB2 divided by Z. And that is the per phase power because I gave you phase voltages. Some people put square root of 3s. You didn't need it because you had phase quantities there. The other thing, too, that people got a little messed up on, they solve for the current I being VB1 over Z. What's wrong with that?
That doesn't take into account the whole big difference between the two.
Or it assumes that this voltage would be 0. Would you ever design a power system that one of your substations, all the voltages are at 0? It wouldn't do anything useful, right? And what that would tell me is all the power in the system is being dropped in that line. You want as little power as possible to be dropped in the line. So when you calculated the power going from bus 1, it included a little bit of the line losses, but mostly the power is being delivered to bus 2 and whatever loads are attached to bus 2. Okay. And then your S was equal to P plus JQ, which were the answers for P, for B, and C. The only thing I was really focused on for B and C was making sure that those were scalar quantities. S can be a vector. It's got P plus JQ, but both P and Q are scalar quantities, not vector quantities. So I didn't want to see any J terms. Okay. Any questions on number 1? I want the magnitude and angle, if you can get it. Like, remember we did open and short circuit tests? We only had a way of calculating S initially, and then you figured out the angle. But yeah, S has a magnitude and an angle. Okay. Any other questions? Okay. Next problem. Draw pictures 1,000 words, right? This is 100. This is 100 plus J 20. The voltage here, it said 200 volt RMS. I'm a little worried that I may have misled people, but 200 volts RMS is the actual voltage there. Yes, sir. J200. Okay, sorry about that. I missed a 0, or I looked at the ohm symbol and I got too quick on it. So That's 200 volts at an angle of 0, RMS. Some people tried to multiply by the square root of 2 to get a peak voltage. But when we do AC circuit analysis, you always have to use RMS quantities. Never use peak quantities. So if you multiplied by the square root of 2, you got completely twisted in terms of your approach. All right. If I had told you 200 volts peak, then you would have had to divide by the square root of 2. But 200 volt RMS, it's the same thing as our sockets. It's 120 volt RMS. You don't multiply that by the square root of 2. You just leave that alone.
But when you write the equation of voltage with the angle, the peak voltage sign.
If you're writing in the time domain,
Yeah,
so you'd say V of t equals 200 times the square root of 2, either the sine or the cosine, just depending on what your waveform is, omega t plus 0 degrees.
I mean, you use the, if you use the angle, you also use the peak, right? The voltage.
No,
And
no. Because do you remember when we did, when we calculated power, we said P average was equal to V peak times I peak over 2. So we just call that VRMS times IRMS, right? Remember how we did the definition for what RMS stands for a sine wave or a cosine wave? Some sort of sinusoidal function. So the 2 comes because of the distribution, or the square root of 2 comes because of the distribution of the 2 when you calculate average power. Okay. All right, so I said find the total real and reactive power and power factor. I did this slightly differently than I think a lot of you did. I said P of the resistor is equal to V squared, 200 squared over 100. Right? And I can't do the same thing for those. And the reason why I can't do that is because, remember, P is V squared over R and Q is V squared over X. But I don't know the voltages across each of those elements, do I? I know what the voltage is across the series element, but I don't know what they are individually. So at that point, I would be better off to solve for the current. So we'll go I of that load will be 200 at an angle of 0 divided by 100 plus J 20. That's going to give you a current. Then I did P for my load, I load squared times 100, and Q load squared, or Q load is I load squared times 200. And then my S total, PR plus PL plus JQL. That was the total power. If you wanted to do a series parallel or parallel combination for the two, that's perfectly fine as well. But what I'm trying to show you is how you can use those formulas that we'll be using a lot in class so that you'll see I squared and whatever. So really, I should be calling this magnitude, right? Make sure that we're 100% clear. Those are magnitudes of currents and voltages. That's why if you notice over here, I called it 200, not 200 at an angle of whatever. I just said 200. Now, I was surprised a lot of people struggled with the power triangle. The power is always real. Some people had the power triangle going that way, which means P is equal to a negative number. You're going from the origin to the left. Power is always positive, so you have to go from the origin to the right. So this is P total, QL, and that's S total. Now, the next one is got to size a capacitor to improve that to unity power factor. So here is my original power triangle. I want that to go to this new power triangle, which is it unity? Is that correct?
Yeah.
So here is my unity power triangle. So my capacitor, I'm going to find by using QL equals V squared over X sub C, right? So you should be able to solve for x sub c. And x sub c is equal to 1 over 2 pi fc. Should be able to solve for c. Yes, sir.
You didn't go over getting the power back. In part A. Yeah.
Part A. P over S, right? Just the ratio, the real power to the total power. Now, some people, they ended up with negative Q values when they did their work. A capacitor is not going to improve your power factor to unity if you have a negative power factor. It's going to make it worse because you're injecting negative bars into your system or bars into your system, which goes further and further and further away. So the only way that you would actually be able to improve the power factor is when you did your power triangle and Q was a positive number. So I saw a few people on the test with negative Qs. What that immediately should alert you to is, no, I've got an incorrect calculation here. How can I be getting a negative Q and then improve my power factor to unity with a capacitor? I can't do that. That's it for page 1. Questions on page 1? Yes, sir.
Real quick, XC, that the formula kind of cut off there, is 2 pi frequency of the baby.
Yep. We derived that at the beginning of the semester. We came up with how that comes up, how that is developed. But I've been talking to the ECE students, and they've all indicated that they have been doing more AC circuit analysis, right? Used to be like 2 hours, maybe an hour worth, but now you're getting a week or so of AC. So, but my hope is that when I said X sub C, that wasn't a new concept. Yes, sir.
First question, if you use the formula S is equal to V squared over Z, right?
Wrong.
Really?
Right. Because all you're going to get is the magnitude of S, right?
I mean, Z is 100 plus 200J, right?
No, you can't do that. It's V squared over Z magnitude. Remember what we just said over here. I don't know what the voltage drop is across the resistor or the inductor. So it's not 200, right, squared over R. It's 200 over R plus JX. And I would get the magnitude of the terms, and I wouldn't be able to tease it out. So we've never done the equation where we said S equals V squared over Z. It's always P equals V squared over R or Q equals V squared over X. Any questions on the first 2 problems?
So,
Yep.
essentially taking the Q that we got in part A and just taking it to 0.
Yeah, exactly. Because it's unity power factor. Unity power factor means a power factor of 1. What happens when my power factor equals 1 to P and S? They're the same, right? So there's no Q term in there. So your capacitor has to completely cancel out the Q that's demanded for that load. Okay. All right, number 3. So you have a bunch of information. I guess I'll draw the diagram here. So I said pick S base equal to 100 MVA and V base to 20 kV, right? At the generator 1. Then you should be able to see on this region here, you have VB2, and this region over here, VB3. So VB2 you determine by finding the turns ratio, and in this case it's T1, so that's VB1 times 200 over 20, and VB3 is equal to VB2 times 20 over 200. Those are my V bases for my system. Now I can pretty much calculate all my parameters. So xg1 is going to be equal to xg old, right? Which is whatever the value you have in your table, multiplied by VB old. I'll just call it VB old, divided by VB1, which is the new base quantity. Let me clean up the old. It's hard to read. Divided by VB1 squared, and then I multiply that by SB new over SB old, and that gives me my updated value. A number of you said, we'll call that XG1 in ohms. You should not have any units on your per unit diagram. That's the whole purpose of per unit, right? Is to get rid of the units, because once we get rid of units, then we can get rid of transformers and our calculations get a lot easier. But in your per unit diagram, I didn't want to see a single unit. No ohms, no volts, no power, no MVA, none of that stuff. Okay. So you have to do the same thing for XG2. And I'm not going to show all those out. Whoops. It's so slow. It's the same calculation over and over and over again. XG2, XT1, XT2. My line, I gave it to you in terms of 120 ohms. So I'm not converting that from an old base to a new base because it's not on an old base. It's given to you in ohms. There's a unit there. So because there's a unit there, you have to convert that to per unit by dividing by Z base in that region. That is VB2 squared divided by S base. A number of you tried to convert 120 ohms on an old base to the new base. So my question for you is, I had a line that was rated for 200 kV, but it was telling you in ohms. What was the S base that you used when you had to try to convert that 120 ohm into a new system, and the new S base? You didn't have an old S base, so how could you pick or use an old S base if one wasn't provided? But you wouldn't do that anyway because it's in 120 ohms. It's the actual resistance of the line or impedance of the line. The last thing was I gave you power. So S, this is really acting slow, sorry. S of the load is equal to 48 megawatts plus 64 megavar. I had to divide that by 100 MVA. And over here, I included the J 0.64 to make sure that you knew that that was a reactive term, that that was just purely reactive. That was it for number 3. Questions on number 3? Yes, sir.
Where's that formula that gives the mass load come?
The formula? What formula?
I'm confused how you have to divide those two numbers by that.
Well, remember in a per unit diagram, it has no units on it, right? So how do you get rid of these units? You divide by your base quantity. Just like we did for voltage, just like we did for current, just like we do for impedance. Whenever you're trying to go from an actual quantity to a per unit quantity, you have to divide by the base quantity. That's kind of the standard per unit approach. So it applies for all units. Okay. We talked about this in lab too, and they said, or even in class, we talked about constant impedance or constant kVA loads. Just treat this as a constant kVA load, and then it's just 0.4 plus J 0.64. Okay. Any other questions on number 3? Continue. All right, let's go to number 4. Number 4 probably appeared to be really difficult. But it actually wasn't too bad. If you recognized, so this is, we'll call this 208, that you're trying to calculate the current flowing in that element there. Or maybe you could even say there if you wanted to. Either one's fine. Well, this is very difficult because if you did this current, right, you actually have a combination of currents over here, and then you also have that impedance element. So what you're better off to do is to convert that to an equivalent single phase representation. And most of the time, it's very helpful to convert your load into a Y connected circuit, because each one of these is going to look the same. But now we know that this is 0 volts, reference to ground. So this voltage over here, because I showed you the voltage across these was 208, the actual voltage from here to neutral was 208 divided by the square root of 3, or 120 at an angle of 0. So all you needed to do for this problem, here's my circuit. This is 1, J2. This resistor gets divided by 3. That inductor gets divided by 3. That's the circuit. Can you calculate the current here? Just a series circuit, isn't it? Should be able to pretty quickly calculate the current for this one. Yes, sir.
How do you go from that one?
How do you go from delta to Y?
Yeah.
You divide by the impedances by 3. Yep.
And then the voltage?
You divide by the square root of 3 to go from a line voltage to a phase voltage. You're not going from delta to Y, you're just measuring off different points. Okay? So that gives you I, and then the total power is here. Once you have that, and you know the voltage here, right, you should be able to calculate the voltage, which is 5 plus J6 times the current you had. Then this is a phase voltage. The line-to-line voltage is just square root of 3 times your phase voltage. And all I needed was the magnitude of the voltage. You didn't have to worry about phase shifting it, because you could get confused if it's positive sequence or negative sequence. So I'm like, just give me the magnitude of the voltage.
Which means the line voltage on the impedance is 208.
No,
So this multiply by square root.
no, 208 is all the way over here. That's on the head of the line. The voltage I was looking for was actually across one of the legs of the delta. That's why I said the line-to-line voltage at the load terminal. Not at the source, but at the load. Right? Because you get a voltage drop across your line. So the voltage gets reduced. Questions on number 4? No questions? Okay, number 5. So number 5, and I'm not even going to bother showing the current sources because they actually don't have anything to do with it. Right, because we're calculating an impedance diagram. And I've got this. And a line over here. And lastly, a couple arrows. Well, the first thing you do is I'm trying to build Y bus. So the load here and here are not part of Y bus. Those are just loads. Those are not part of the system. Those are interconnected loads. So in terms of affecting Y bus, they have zero impact, none whatsoever. So you can throw those away. They have nothing to do with anything. Now, the next step you had to do, I gave you these as Z. So let's look at the first one. How did I know that this was a Z? Because does an inductor have a positive or a negative J term? Positive J term, right? For the impedance, for the inductor. So the Y here is 1 over J.25, which is negative J4. So now to build Y bus, you're going to start by Y of 1 comma 1. I'll call YB, which is equal to, we'll call this Y1A, Y1B. So Y1A plus Y1B plus Y1 to bus 2 plus Y1 to bus 3 plus Y1 to bus 4. Just add them up once they're inverted. Then we'll do the same thing for bus 2. That's going to be equal to Y2A plus Y2B plus Y12 or 21, right? It's the same element, doesn't matter. Plus Y24, and there is no connection between bus 2 and bus 3. Y bus 3 comma 3 is going to be equal to Y3. I've only got one element connected there. Plus Y13 plus Y 3, 4. And lastly, 4 comma 4 is equal to Y4 plus Y1 Y 4, but Y14 plus Y24 plus Y34. And those are my diagonals. The off diagonal, so I'm just going to put YB, and we'll just call it off, is equal to the negative of the transfer admittance. So YB of 1 comma 2 is an off diagonal because the 1 is a 1 and a 2, not a 1 and a 1. That's equal to the negative of Y12. YB13 is a negative of Y13, and on and on and on and on and on. And I didn't ask you to build, well, I mean, solve for Z bus. So remember there was questions before the test. Are we going to have to invert a Y bus matrix with complex numbers? No, you just needed to add or subtract as necessary. That was it for number 5. Any questions on number 5? All right, last question then. Oh, yes, sir. No. Yep. No, all the elements on the diagram were given in terms of Z's. So you had to invert every element on the Y bus diagram to get Y's.
Oh, who's got Y right there, 1 over.
Yeah, because that's the inverse of the impedance or the reciprocal of the impedance between bus 1 and 2. So I have J.25 as the impedance between 1 and 2. So to get the admittance between 1 and 2, I had to invert the whole thing. Because J 1 over j is equal to negative j, right? If you remember back from whenever you did complex numbers. Okay. Number 6. We had a bunch of tests. This was a single phase unit. V open circuit, I open circuit, P open circuit, P short circuit, I short circuit, and P short circuit. And I did all these on the on the high voltage winding. So the open circuit test is going to give us RC and JXM. So let's draw our power triangle. This is P open circuit, V open circuit times I open circuit. That gives me a theta open circuit. So my Y open circuit was I open circuit at an angle of minus theta open circuit divided by V open circuit. And that's going to be equal to 1 over RC plus 1 over JXM. That gives you your open circuit parameters. Your RE and JXE, same process, but now these become short circuit. So, in this calculation, because the elements are in series with each other, I don't do Y, I solve for Z. So Z short circuit is V short circuit divided by I short circuit at an angle of minus theta short circuit, which is equal to RE plus JXE. Notice I said V short circuit because both of these are at an angle of 0. Those are our references. That was the equivalent circuit model. And that looks like this, right? RE, JXE, RC, JXM. For part B, it said, if I neglect R sub C and JXM, now my circuit looks like this, right? And it says, assuming that the transformer is operated at full load, okay? Full load, which means the load connected to this is 50 kVA at a 0.8 power factor, right? So I know that this is 2400 at an angle of 0. I have an RC and a RE and a JXE. I can solve this equation for I, right? Because S equals VI conjugate. So I is equal to S divided by V conjugate, correct? And what is my S value? I get that from the 0.85. Now, I know that P out is 40 kilowatts, right? Because P over S is equal to 0.8, which means if S is equal to 40, then 50, then 50 times 0.8 is 40. So that's 40 kilowatts. Now I got I squared R losses here. So input power is equal to P out plus the magnitude of I squared times RE. And can you correct me if I'm wrong? Because I talked to an ECE student earlier, and they said that they are not familiar with efficiency equations. You're not familiar with efficiency? So when they talk about an amplifier, they don't say how efficient an amplifier is?
Pretty rarely.
Is that true for most of the ECE students? Because that's really almost shocking to me that you wouldn't know what the efficiency calculation is. Again, not a put down on you. It's more about whoever's teaching it.
I think it was covered at some point. It's just, I know it's kind of simple, so I think they probably said it like once. Like it's a fraction of power out over power in, and then they never touched it again. And no one.
So maybe they just assumed that you would know it from previous stuff, because it's probably something you even did in physics in high school, if I had to guess. Because again, this is not a put down on any of you all. It's a pretty simple, like you said, calculation, right? It's just P out over P in. and mechanical systems?
Yeah.
So that it kind of just lost the.
Okay. Yeah, well, I didn't mean to be, I just assumed everybody had been exposed to it, so I'm surprised. I'll talk to EFANG and just ask them to kind of maybe just consider adding some efficiency stuff, because it's pretty darn important, right? And it's only P out over P in. It's not S out over S in. Why is that? Yes, it determines how much power is wasted, right? So the efficiency of a system is determined on how much power you put into it is being converted to useful work. Not imaginary power, because imaginary power is going back and forth, right? So that's not wasted energy. So that's why it's got to be P out over P in, not S out over S in or Q out over Q in.
I don't remember it being covered in some class before, but definitely not in that, that being, it's just the real power.
Yeah, I'll talk to EFANG. So all ECE and non-ECE students all take 209 and 210 now. They don't have the service class to non-ECE majors anymore, or do they still do that? Who are non-ECE majors in this program or this class? No. So do you guys take the same ECE class that the ECE students take? Or is it a service class that does all topics? Do you know? So you took the regular 210? Okay, but there is did you take 209?
So, yeah, they just made.
Also, they don't differentiate anymore.
No.
Okay.
Last month's big. I had.
Okay.
But 209 was like historically what the mechanical.
Well, it's ECE for non-ECE majors, basically. It's not that it's not as good. It's just less, they have broader topics, so you don't dig down into the topics as much as maybe the ECE students might need. But you would cover more, you might even cover op amps and BJTs and stuff like that. You would do electronics. So it's almost like setting you up for the FE perhaps. So that's probably the difference. But if 210, that's a good thing because they would cover some AC, but then unfortunately you lose out on some of the other stuff that would be good to have, so. But in 209, for those of you who took 209, well, nobody took 209, right? You took 209, do you remember if they covered efficiency in 209? Okay, yeah, I'll just ask them if they can emphasize, because it's not a hard calculation, but it's pretty darn important when you get out in the real world. Even when you buy, your car, right? How efficient is your vehicle from converting a chemical material to power? But in mechanical systems and chemical systems, it's a lot easier. In electrical systems, it's much tougher because there is no such thing as borrowed power, right? You don't really have those concepts, so it's very different. Yes, sir.
Calculate power in, power out, and when we put them over each other, we just calculate like a percent error kind of thing. That's the only thing I really do.
Well, when I think of percent error, I think of what the actual calculation would be and what you got. But to me, this is not a percent error. This is like just how much power or energy is wasted. So I just have to get clarification on that. So I'll talk to EFANG and see if I can get clarification.
Maybe that's not the part.
You couldn't find it. Okay, yeah. Now do you see how to find the current? It's much easier when you make them simplified series circuits, right? I forgot to do the last part. Last part, I needed a phasor diagram. What are the only two phasors in this class? Voltage and current. Here's V, and here is I. I don't want to see a circuit diagram. I wanted to see a phasor diagram. And the only two phases we have are voltages and currents.
What about the power diagram?
Don't want the power diagram either.
Power, phase, I'm like, what's this again? Just.
No, and phasors are really important to us because when we start looking at power flows, we really will need to understand magnitudes and angles. And getting those relative terms is really, really helpful for us to understand and troubleshoot things. That was it for the test. Average was an 89. there was a built-in bonus feature. You could, I think, got 35 additional points on the test. But that does not mean your score is based out of 135. So take the score that you have, that's your score. You don't need to divide that out of 135. So there were people who got more than 100% on this test. If you look in gradebook, they can get more than 15 points for the total final grade. Because somebody said, do I do a curve and all that stuff? I don't like doing curves because I don't want people to feel like they're given anything. And here you earn it. You earned your grade. Every point that you got is earned. I feel a lot better about earning something than being given something, especially where it translates to knowledge, hopefully. So to me, I'd rather have you earn what you get as opposed to be given something. I don't know how I know in EC sometimes the averages are 30 or 40. And so they got to put a huge curve on it. But I think that is discouraging. And also, like, what did you earn? Hey, a 30 translate to a 76. Did I really earn that? I don't know. So this way you earned all your points. So hopefully you feel better about yourselves. There's more work, right? Like people taking the test were like, can I be done at this point? But you get opportunity for extra points. Yes, sir.
I don't understand, how does your grading system work with the point in 135?
So there's a total of 135 points. So if you got 135 points total on this test, your grade for the test, for all intents and purposes, is 135 out of 100. Not 135 out of 135. So whatever you got was the accumulation of your points. That's your score. Yes, sir.
One-time thing, or do you do it for every exam?
I will probably do it for every exam because I love you all to earn your own points. Unless everybody hates the idea. But I really like having people, you earn what you got. That's the rest of your life is you earn something. Nobody's going to say, well, you deserve 10 more points because I like the way you look. You're going to say, no, you have to do it. You have to earn those. So that's the way I like that. Yes, sir.
One more question, that's the crazy diagram from.
Yes, this is part B or C.
So that's all you would.
But I wouldn't need the actual magnitudes and angles. Yep. That's all I had. You guys had a really tough exam yesterday, so I'm not going to cover new material unless you want me to. I'll let you out early. Yes, sir. You might need to tell me when to stop. Yeah. Right here? Yes, sir.
Posted numbers.
No. I don't post the numbers because I encourage you to go through the test, get the numbers, and it's going to help you learn.
And if I like take a problem I did wrong and try to redo it, how do I know if I did it right?
If you want to come see me and say, did I get these numbers right, or does this look right? Then yes, I can do that. Yep. Yeah, I'm all about you learning the material. So if I just give you the points or the numbers, then you don't go through, right? Human nature is, oh, that looks right. But if you want to learn it, you'll go back and you'll do the approach. That's why I did these all as actual variables. Yes, sir.
For number 3 today, we go over the per unit of the load again. How would on that?
Just divide the S quantities, the 48 and 64 megabar, and divide it by S base.
So that would be like 0.48 plus the J, 0.64.
Per unit power.
So you can have J in your.
Absolutely. S is a complex number, isn't it? As P plus Q or JQ. So yeah, S can have complex, can be a complex number.
Yeah.
But P and Q cannot.
I see. Really quick on that, Nick. I guess what would our answer kind of look like for that question? Not like the numbers, but
I would redraw the diagram
redrawing it at that by.
without any of the transformers in it. Right? Because once you go to per unit, transformers are gone. so they don't exist.
And so that would be like a closed circuit.
No, it's exactly like this, sans the transformers. Yeah, it's just a line with the transformers and the line impedance is all shown there. Yes, sir.
So what's that load per unit power? and
Yes.
impedance?
How could it be impedance if the units are 48 plus J 64 megavar? How could that be how could that be impedance?
But, I guess part of my mind is I was trying to find the impedance.
Nope. You could have tried to convert it to a per unit impedance number, but then you would have had to assume that the voltage was fixed. And then you have to do the V squared over R and the V squared over X to get V squared over P and V squared over Q to get the R and the X value, and then divide that by Z base. But in reality, most of our loads are going to be considered constant power. So you just divide by S base. And if you look back at one of the labs, we talked about how to do that in the per unit lab. You had a couple options.
Do you ever do a per unit with voltage?
Yeah, all the time. The V base 1 and V base 2 that VB1 and VB2 we did on the first problem almost never would be written as those voltages. It would be 1.03 at an angle of 22 per unit voltage. Yeah, all your calculations on the power system are all done in per unit because it's too much work to transfer stuff over our transformers. So all the calculations will be done in per unit. Voltage, current, impedance, and power, all those are done in per unit. If you were to look at a per unit diagram under the hood, if you will, of a power systems analysis program, they're all without units. Anything else? Yes, sir.
Right, I went back to 6E, we had a first put in it somewhere on the right side. I was completely running a little bit strange. So the magnitude of power over voltage is conjugate sometimes.
Yeah, because S equals VI conjugate, so solve that equation for I. So I just put the parentheses around the S and the V.
I just got confused because of the other side, bar there.
Okay. Yeah, it's S over V.
Is that little line next to the S, what's the its magnitude?
That shouldn't exist there. That's just a relic of. Well, let me just erase it all here.
And the 50 kilovolt amps at something, what's the thing that next to it?
0.8 power factor. Yes, ma'am. Which one? For C? Let's see, that's the voltage one right here, yeah. So you solve for the phase voltage, and then you multiply that by the square root of 3. Because I wanted the voltage at the load, not at the line. I already knew what the line voltage was, it was 208. But the load voltage, I did not know, so I wanted to calculate that. And it's actually going to be, it's actually going to be quite a bit less than 208 because the load is 5 plus J6. That's not that much bigger than 1 plus J2, right? So you're going to get a pretty significant voltage drop across the line. Does that answer your question? Sure. Anything else? TV land? Silence. All right. Well, everybody have a wonderful day. Enjoy the weather, and I will see you all on Thursday. Take care, everyone.
Thank
See you,
you.